Swayam Prabha. Digital India. Educated India.
So we will continue our discussion moving on to section 3 now, which is the analysis of heat exchangers. We are on slide number 44. So now whenever we talk about heat exchangers, there are essentially two types or two major classes of problems in heat exchanger design and analysis. As an engineer, you often find yourself in a position where you need to either select a heat exchanger that will achieve a specified temperature change in a fluid stream of known mass flow rate. That means the fluids are known. What type of, suppose for example, you may have some, let's say, industrial hot water is available, and let us say some stream of water in a river or a pond is available. Air in the atmospheric this thing is available, and you need to cool down a certain hot water which is coming from some plant. So this is where you will do the sizing problem. So such type of problems are called as sizing problems, wherein you select a heat exchanger that will achieve a specified temperature change. That means the delta T of the hot fluid or the cold fluid, whatever is the objective function, is specified to you. The client wants a particular delta T. He knows at what temperature the thing comes out of a system, and he wants it to cool down, or he or she wants it to cool down to a certain temperature range, and that is specified, and therefore you have to do a sizing problem. Now such type of sizing problems are dealt with by the method of log mean temperature difference or logarithmic mean temperature difference, or the LMTD. So we will of course spend a considerable amount of time on understanding this LMTD method. You already know the definition of LMTD. We will again go through it quickly in the next lecture, and then apply this method to find out how we can do the sizing of a heat exchanger. Now the other problem which can occur is that if you have a specified heat exchanger, that means the heat exchanger is available to you. You are supposed to predict the outlet temperature of the hot and the cold fluid stream in a given heat exchanger. So these type of problems are called as rating problems. So you have to rate the heat exchanger, which means that you have to predict the outlet temperatures, that what will be the temperatures if these two fluids pass through it in a certain mass flow rate. So such type of problems can be solved by another, let's say, elegant method, which is called as the NTU effectiveness method. So after we study the LMTD method, we will also study the NTU effectiveness method. So NTU means number of transfer units, and we will of course spend a considerable amount of time after these lectures to understand this effectiveness of a heat exchanger, and NTU. What is NTU? The non-dimensional quantity, and we will see how we can use it to analyze the heat exchangers. So moving on to slide number 46. So we will be essentially doing these two types of problems in the next couple of lectures. So what do you mean by design or analysis of a heat exchanger? So to design or to predict the performance of a heat exchanger, it is essential to relate the total heat transfer rate to quantities of interest such as inlet and outlet fluid temperatures, overall heat transfer coefficient, and the total surface area of the heat exchanger. So when you do the sizing problem, you are actually predicting the surface area, what will be the total area required, or what will be the length of the tube required to attain a certain heat transfer. Since the mass flow rates are known, you can get the Reynolds number of the flow because the geometry you are choosing the type of heat exchanger which you would like for a particular duty. So it's an iterative process, of course, but nevertheless, you want to sort of relate the heat transfer coefficient, the mass flow rates, the geometry of the system, the configuration of the device to what is the performance at the end, how much heat you are able to achieve in a given under the given boundary conditions. So for such type of problems, as we said, the LMTD method is a simple approach when the fluid inlet temperatures are known and the outlet temperatures are either specified by the client or readily determined from energy balance expressions. So when these temperatures are known, the inlet temperatures and the outlet temperatures, or what is the expected outlet temperature, if this is specified, then we will use, as I said, the LMTD method or the logarithmic mean temperature difference method for this class of problems, the sizing problem. Then it is also used for determining the size of the heat exchanger. That is what I am saying, sizing, to realize the prescribed outlet temperature. So for example, if you know the inlet temperatures and for a given size of heat exchanger, the outlet can be predicted. But then if that doesn't satisfy the client, then you need to increase the area so that there is more residence time inside the heat exchanger, and so you will get the desired outlet of either the hot fluid becoming colder or the cold fluid becoming hotter, whatever is the main objective function. You achieve that by the sizing problem. So these are this is how you will proceed. So let us try to understand it more, let's say, clearly in the next slide, which is slide number 47. Also, you must remember that, let us see under what assumptions we will do this analysis. So there are some major assumptions. The first one, of course, is to note that the heat exchangers usually operate for long periods of time with no change in their operating conditions. So more or less, once they are designed, they will continue to operate. Of course, as we have studied in the last lecture, the fouling may take place over a period of time and the performance may decrease a bit. But then routine maintenance is done to clean the heat exchanger also. So almost all heat exchangers are modeled as steady flow devices. So we are usually not bothered about the transient of the heat exchanger because it is small as compared to the total time in which the steady state operation is desired. In fact, it is minuscule, the transient. Then the mass flow rate of each fluid remains constant. Typically pumps are used to supply the liquid unless there is a change in, let us say, the mass flow rates are not, let's say, moderated very frequently. But sometimes there is a change in the river water temperature, for example, and then the mass flow rate may have to be changed. But for most practical purposes, for hours together, the inlet velocity or the mass flow rate of the cold and the hot fluid will remain identical for continued period of time. Then the fluid streams experience little or no change in their velocities and elevations, and thus the kinetic energy and potential energy changes are also negligible. So this is also a common assumption under which we will do the following analysis. Then the thermophysical properties like specific heat of the fluid in general changes with temperature. We all know that. However, sometimes the temperature change may also be large, but for a given range, it can be treated as constant at some average value with little loss of accuracy. So for most analysis, we will assume that the thermophysical properties are constant. So some more assumptions are given in the slide number 48. That means one of them is that the axial heat conduction along the tube is usually insignificant. We will neglect it. And the outer surface of the heat exchanger is usually assumed to be perfectly insulated, so no heat loss. So essentially what is happening is the hot fluid loses its heat to the cold fluid, and whatever energy exchange takes place, it takes place only between these two flowing fluids and not with any other third party or third environment. So it is only the mutual. So what is lost by the hot water is supposed, or hot liquid is supposed, or hot fluid is supposed to be taken by the cold fluid. So these idealizations which are stated above are closely approximated in practice and hence are commonly employed. So most of the assumptions which we have seen are quite true, and under these assumptions our analysis will be based and we will get reasonable answers with such type of assumptions. The assumptions also make the analysis simpler yet meaningful. So we don't have to complicate it unnecessarily, and we need meaningful, let's say, performance parameters or sizing of the heat exchanger. And then of course at the end one can always do some factor of safety for taking into account some transients or some variations which might take place, and try to design a conservative estimate which is also economical, reasonably economical in nature. So under these assumptions, let us apply the first law of thermodynamics. So essentially what it requires is that the heat transfer from the hot fluid is equal to the rate of heat transfer to the cold one, because these are the only two elements which are exchanging heat with each other. So this is done in slide number 49. So here you see the rate of heat transfer in the heat exchanger when the heat exchanger is insulated, as we have just assumed, is Q dot is equal to U, which is the overall heat transfer coefficient, which takes into account the convection, all the three resistances or even 5 resistances depending on whether fouling is also taken into account or not. So all the possible resistances which are coming in the direction of this, in the path of this Q dot, are taken into account in this U, into the area which is the appropriate area of heat exchange, and then delta Tm. So delta Tm is the appropriate temperature or mean temperature which is applicable throughout the heat exchanger. And we have seen earlier that it is the logarithmic mean temperature which is the true, let us say, indicator of the mean temperature, because as you are aware, the mean temperature actually changes in a typical heat exchanger as it flows. Now under certain circumstances, the mean temperature may not change also, which we will see soon. So in general, this U, which is the heat transfer coefficient, and delta Tm change along the heat exchanger in general. Of course, the area of the heat exchange AS remains constant once the heat exchanger is defined or designed or it is chosen. So now let us quantify further what happens to the individually to the two fluids which are flowing. So you can write Q dot is equal to m dot C. So the C, let's say, the subscript C corresponds to the cold fluid. So Q dot is equal to m dot C. This is the mass flow rate of the cold fluid, into CPC, which is the specific heat of the cold fluid, into TC out minus TC in. So that is, the cold fluid will become hot and therefore TC out will be hotter or larger than, its value will be larger than TC in, because the cold temperature will cool down, will become hotter as it passes through the heat exchanger. So this is the heat which is absorbed or taken by the cold fluid. Now this must be equal to what is lost by the hot fluid, and naturally the delta T here will be TH in minus TH out, because the inlet temperature of the hot water or the hot fluid is higher than its outlet temperature as it passes through the heat exchange. So this much amount of heat, which is exactly equal to the what is gained by the cold fluid. So these two equations must be identical. And in the heat exchanger analysis, it is usually very, let's say, convenient to sort of club the m dot C, which is the thermal mass. So m dot is the mass flow rate and Cp is the specific heat. So mass into specific heat is the thermal inertia, indicator of the thermal inertia or the thermal mass of the system. And we usually club them and call this and term it as capital C. So this small c is the specific heat at constant pressure of the liquid or the fluid, and this Ch is the thermal inertia, which is so m dot h into Cph, and similarly capital Cc will be equal to m dot C and Cpc. So you can write this equation as Q dot is equal to Cc into delta T cold, and that is also equal to Ch into delta Th. So moving on to slide number 49. Now, so as we have seen, it is convenient to combine the product of the mass flow rate and the specific heat into a single quantity, which is called as the heat capacity rate. Now, the heat capacity rate of a fluid stream represents the rate of heat transfer needed to change the temperature of the fluid stream by 1 degree as it flows through the heat exchanger. So this is the mass flow rate multiplied by the specific heat, and therefore it is, in other words, it is the amount of heat which is required so that the temperature changes by 1 degree centigrade. So what will happen now? Suppose we are comparing the heat capacities of the hot fluid and the cold fluid. So naturally, for a heat exchanger, the fluid with a large heat capacity rate will experience a small temperature change because its thermal inertia is very high, the m dot is high, the Cp is high, or the multiplication of the two, which is the heat capacity rate, is actually high, and therefore it experiences a smaller delta T. So please note that as soon as you have a higher thermal mass, then it is natural to say that this particular fluid out of the two, out of the hot and the cold fluid, the one which has a higher heat capacity rate will have a smaller temperature change, and vice versa. So now what happens if Cc is equal to Ch? So just to look at this diagram here, it's a counterflow heat exchanger, and you can see that the delta T1 and delta T2 are actually identical. Why does it happen? Because Ch and Cc are the same. So if Ch and Cc, the capital Cc and capital Ch are the same, or they are identical, then what will happen is that the delta T's will also be identical, and it will be a constant temperature change between the fluid. That means as you pass through the heat exchanger, the delta T remains identical. So whatever is the inlet delta T remains throughout in a countercurrent heat exchanger, for example. So delta T is equal to delta T1 is equal to delta T2, which is equal to constant. So the only time the temperature rise of a cold fluid is equal to the temperature drop of the hot fluid is when the heat capacity rates of the two fluids are equal to each other. Otherwise, in all other cases, and this is true for any type of heat exchanger for that matter, and for all other conditions, and then mind you, the capital Cc can become equal to capital Ch by the combination of mass flow rate and specific heat. So in certain cases mass flow rate can be low, but the specific heat actually is high, and therefore the multiplication comes to a value which can be made equal to the hot fluid value, and vice versa. So keep this in mind that the only time this can happen is when the capacities rates are similar or identical. Now, as you will recall, we have discussed so far only those heat exchangers where sensible heat transfer takes place in both the fluids. But as we have also noted in the earlier lectures, some of the heat exchangers can have boiling and condensation also, and the heat capacity rate of a fluid during a phase change process must approach infinity since the temperature change is practically zero. So you can see here a condensing fluid, there is the delta T is practically zero, and therefore the heat capacity rate is approaches infinity theoretically, and similarly in a boiling liquid also, the fluid is boiling, the hot fluid is undergoing a sensible heat transfer. It can be air, for example, and water can boil because hot air is passing over it, and water will start boiling at a constant temperature, and therefore the heat capacity rate of the boiling water here will tend to be let's say theoretically as infinity, because the delta T is actually zero, and whatever heat you supply from the hot fluid to the boiling fluid, it will directly lead to a phase change process, and therefore Q dot is equal to m dot HFG will be the guiding equation as far as those heat exchangers where phase change is happening. So with this background, we will now start the LMTD and the NTU effectiveness method, understanding them. What we have understood in this lecture is that sizing and rating are two important problems in heat exchanger design. The heat capacity ratio is also a very critical and important parameter for analysis, and we will continue to use it in both the methods. And the appropriate form of mean temperature difference between the two fluids exchanging heat with each other in a heat exchanger is logarithmic in nature. We have also specifically proven this when we were doing internal flows, chapter 8. And we will again do it once again for your clarity in the next lecture. So with this we close micro lecture 3 at slide number 53.